Okay, yes, this next topic is quite a biggie, so I wanted to start a new video and make sure that I won't be rushed on this part. So we're going to talk about an issue related to significance, and in particular, how we can measure whether a number is significantly small or large. It's something we'll keep doing for the rest of this course. Um, so remember, when we talk about significantly small or large, that really has two requirements to it. It needs to be large. Let's just do an example with large. And remember that, do you remember where the large numbers are when we look at a two-dimensional graph on a histogram like this one? What numbers do we consider large? They're the numbers that are far to the right. And by the way, today's analysis applies specifically to unimodal distributions, those that have one peak that's not on the far left or right extreme. So basically bell-shaped curves, and that's what we're going to be concentrating on in this class. So when you have a bell-shaped curve like this, your most typical scores are in the middle. Those that are large are far to the right. In order to be significantly large, we need a number that is not only far to the right, but also uncommon, or having a low probability or percentage. And how do we measure that on a graph again? That means short, the short bars, okay? And as a default value, excuse me, remember that we usually use the measure of the value of about 0.05, about 5% is kind of our cutoff for unusual values. So suppose that we're looking at this graph of the binomial distribution of flips of a coin. This graph again says if we flipped 15 coins, how many heads would we expect? And you can see that the most common expected values would be 7 or 8. My question to you for this example will be the following. What about 11? 11 heads. Would it be considered unusual to get 11 heads? And if so, would that make 11 significantly large? Based on what we've discussed in this class so far, you might think that the answer is a very simple yes. You might say, well, look, 11 occurs with less than 5% probability, and we've decided that that makes it unusual, and it's kind of far off to the right, so that makes it unusually large. But this might surprise you, but the answer is going to turn out to be no. This is not considered unusually large. And that is because if we just look at the 5% cutoff, that really only tells us how probable this exact number of heads is. But that doesn't give us a sense of how large that value of heads is. Okay, so that we're only getting half the picture there. To give you another illustration of why we can't just look at the height of the bar, consider a distribution that didn't have 15 numbers in it, but like 50. If these numbers went from 0 to 50, then on the average, every single value in the distribution would occur approximately 1 out of 50 times, which is 2%. So that would really make every individual value unlikely. And that doesn't mean that every value is unusually large. It just means that there are a lot of possibilities. So any particular value would just be 1 out of very many. So, for example, what's the probability that somebody was born on July 15th? Well, it's only 1 out of 365, but that doesn't make July 15th a really unusual day, because that's the probability for every day of the year. 1 out of 365. So we need a better way to combine these two qualities of being relatively large and relatively improbable. Okay, so I hope I've stated the problem well enough. here's the solution. It might surprise you, but I think it's a reasonable solution. And the solution is, rather than just looking at this one bar, we actually look at the value of all of the values that are at least as large as this bar. It's called a tail value because if you look at 11 flips of the 11 heads out of 15 coins, we want to think about this 11 as basically the borderline between all the values that are this big or bigger. So 11 or 12 or 13 or 14 or 15. All right, so to measure how unlikely it is to roll, I keep saying roll like I'm rolling dice, flip. To talk about how probable it is to flip 11 coins, we're really concerned with all the values that are 11 or more, at least 11. Okay, so that's basically what I'm stating in my notes here. To evaluate whether a number within the list is significantly large, in this example, we don't just look at the probability of selecting that number, we look at the probability of selecting a value at least as large as that number. So and in this example, that means 11 or 12 or 13 or 14 or 15. And the way I've stated that in English, I kept using the word or. Tell me again, what does or mean? Plus. Okay, so what we're going to do is add together all of these values to get what's called the tail probability. And I'll go ahead and pause and do this on my calculator. If it'll let me pause. There we go. Okay, I've done that calculation here. The probability of flipping 11 or more heads, it adds up to about 5.9%. If you add all these probabilities together, you get this tail probability of 0.05921 or 5.9%. And that's above our 5% threshold. So this is the relevant value that we use to decide that 11 is actually not significantly high. It should be clear to you that 12 is, because if we add together the 12 or 13 or 14 or 15, we're going to get something barely more than 1%. So that would be significantly high, but the 11 would not. Now, as far as notation and terminology, this tail probability, it's a really important concept in this class that we're going to see many times again. So let's give it a name. It is called the p-value. So p basically, I guess that just stands for probability or proportion. So it's related to a percentile. So let's make sure that we can clarify the difference between a percentile and a p-value. The percentile is the percentage or area of all the values to the left of x. So basically what's shaded in blue here would really be considered the percentile for 11. The p-value is the area of a tail that is cut off by our value of interest. So the pink shaded part here is the tail that's cut off by the 11, and that is the p-value. Okay, so again, percentile is always to the left, p-value is always a tail. Now, as it turns out, we are going to see that p-values can be right-tailed, or they can be left-tailed. There I've shaded an example of a left tail, so that would be a left p-value. And sometimes we even do a two-tailed p-value. So look for those terms in the weeks coming up. Left-tailed, right-tailed, two-tailed. Those are the possible different shapes for a p-value. But no matter what side it's on, it's always a tail. Okay? It's always kind of the extreme end. As opposed to the percentile, which is always to the left. Now, to decide whether the tail is small, unusual enough, we have to compare it to a significance level that is determined in advance. And again, the default would be 0.05. Sometimes it ranges between 0.01 and 0.1. But there's a name for that significance too, and that's alpha. The symbol for significance is alpha. So we're learning a bunch of really meaty new concepts here. P-value, significance alpha. If the p-value is less than alpha, that tells us that the value is significantly large or small. This is a lot to think about. You're not going to be tested directly on all of this week, but it will come up a lot in this course. So this just felt like the right moment to me to kind of introduce this idea. What you will be tested on this week is how to calculate a tail probability on a histogram like this one by adding the last few bars, or the first few bars if you're looking at a small value. Okay. Thanks for listening. See you next time.